We present to you an ankle impedance control strategy for downslope walking with a transfemoral prosthesis. The current state-of-the-art impedance control strategies don't enforce continuity of stiffness and damping functions across the gait cycle. Few have looked into downslope walking and reported gait kinetics. Generally, they have numerous tuning parameters. Now, our objectives were to derive continuous nonlinear stiffness and damping functions for a prosthetic ankle on downslopes, and use principal component analysis to simplify these functions and derive a rule base for designing impedance controllers for any downslope angle. We first split up the gait cycle into 4 phases. We also observed that these 4 phases tend to change based on the slope angle. Now, these phases help us set up a finite state machine and implement impedance control strategies. We then create an optimization problem where we minimize the difference between human torque data and the torque from an impedance controller. We also have some continuity constraints on the stiffness functions and the damping functions. Here, our stiffness and damping functions are polynomials during the stance phase, and they are constant during the swing phase. Here are the resulting stiffness and damping functions, and on running a principal component analysis on them, we got these principal components, and the weights have been shown on the right. Notice there is a linear trend in the stiffness component weights. Now, these trends can be used to design a downslope walking controller for any slope angle. But you have to tune it a little bit. So notice here we do not have any mid-stance dorsiflexion in the ankle. By scaling the stiffness and damping functions and tweaking some of the equilibrium angles, we can get the desired ankle dorsiflexion during mid-stance. We did an emulator study with a transfemoral prosthesis on level walking, downslope walking at -5 degrees, and downslope walking at -10 degrees. Notice that we have lesser heel-off plantar flexion and push-off torque as the slope grew steeper. This is consistent with human sloped walking data. Thank you very much. We hope to extend this control scheme to upslope walking and estimate stiffness and damping functions for the knee joint as well.